All right, today we're jumping into a really cool piece of calculus called Rolle's theorem. And I know, the word theorem can sound a little stuffy, right? But what if I told you it's not some dry, dusty rule? It's actually more like a mathematical promise, a guarantee that if you set things up just right, something very specific has to happen. So, what's this big promise all about? Let's find out.
So, to really get this, let's start with a simple question. Picture this. You're out on a hike. You start at a certain elevation. Maybe you go up a big hill, down into a valley, but when you finish your hike, you end up at the exact same elevation where you started. So here's the question. Is it an absolute guarantee that somewhere along that path you had to have been on a spot that was perfectly, totally flat, just for a moment? I mean, think about it. It kind of feels obvious, doesn't it? Well, guess what? Rolle's theorem is the hardcore math that proves your gut feeling is spot on. Okay, so to get this guarantee, there are some rules. You can't just have any old path. Math has some pretty strict terms and conditions. We're going to translate our little journey into the language of math. And these rules basically just describe our hike perfectly. First up, the path has to be continuous. Simple enough, right? It just means you can't, magically teleport from one spot to another. There are no sudden gaps in the trail. Second, the path has to be smooth. In math, we call that differentiable. Basically, no sharp ankle-twisting corners or cusps. And third, and this is the big one for Rolle's theorem, the start and end points have to be at the same height. So f of a has to equal f of b. If you can check all three of these boxes, the promise is locked in. So let's say we followed all the rules. Our path is continuous, it's smooth, and we start and end at the same place. So what? What's the big payoff? What is this guaranteed flat spot the theorem promises? And here it is. This is the core of it. The promise is that if those three rules are met, there must be. And I mean, it's not a maybe or a sometimes, it is an always. At least one point, we'll just call it C, somewhere between your start and end point, where the slope is exactly 0. That's it. That's the flat spot from our height. It's a mathematical certainty. Okay, so what does flat spot look like in the language of math? Well, we call it a point with a 0 derivative. See, the derivative is just a fancy tool that measures the slope, or the steepness, at any single point on our path. So when we say the derivative is 0, which we write as f prime of CD equals 0, all we're really saying is that the tangent line, the line that just kisses the curve at that one spot, is perfectly horizontal. Like the very top of a hill or the very bottom of a valley. All right, that's enough theory for a minute. Theory is great, but let's see this thing in action. Let's get our hands dirty with a real example and watch Rolle's theorem do its thing. Okay, for our experiment, we're going to look at a pretty simple function, a parabola, f of x equals x squared minus 4x. And we're going to focus just on the interval from x equals 0 to x equals 4. So you can think of that as our journey. We're starting at x equals 0 and ending at x equals 4. So first things first, we got to check the rules. Does our function meet the conditions? Condition 1, is it continuous? Well, it's a polynomial, and those things are as continuous as it gets. No breaks, no gaps, nothing weird. So check. Condition 2, is it differentiable? Is it smooth? Yep, for the same reason. It's a nice smooth parabola, no sharp corners anywhere. So check. And now for the big one, condition 3. Is f of 0 equal to f of 4? Let's see, plug in 0, you get 0. Plug in 4, you get 4 squared, which is 16, minus 4 times 4, which is also 16. So 16 minus 16 is 0. They're both 0. So yes, f of 0 equals f of 4. Check, check, and check. We are good to go. The theorem is officially in effect. Okay, so Rolle's theorem now promises us, guarantees us, that there's a flat spot somewhere between 0 and 4. But where is it? To find it, we need to pull out the most powerful tool in calculus, the derivative. The derivative of our function, which we write as f prime of x, is 2x minus 4. And remember, this new little function here is basically our slope-finding machine. It'll tell us the slope at any point x we want. And now for the magic moment. We're looking for the flat spot, right? The place where the slope is 0. So all we have to do is take our slope finder, 2x minus 4, and set it equal to 0. So when does 2x minus 4 equal 0? A little bit of algebra, and you find that x equals 2. And there it is. That's our C. Right at x equals 2, smack dab in the middle of our interval, the slope of the curve is perfectly flat. The promise was kept. How cool is that? So, okay, that's a pretty neat trick for finding flat spots on a graph, but why does it matter? Why is this one theorem so important in the grand scheme of calculus? What's the bigger picture here?
Well, the reason Rolle's theorem is such a big deal is because it's basically the foundation for an even bigger, more powerful idea called the mean value theorem. Here's a way to think about it. Rolle's theorem is the special case. It's when your endpoints are at the same height, and it guarantees you a spot where your slope is zero, perfectly matching the horizontal line connecting those endpoints. The mean value theorem is the general version. It works for any two endpoints whether they're at the same height or not. It guarantees that at some point in your journey, your instantaneous slope, your steepness right at that moment, will perfectly match the average slope of your entire trip. It's a huge deal.
So let's wrap this up. We've seen that Rolle's theorem gives us this amazing guarantee. For any smooth, continuous trip that ends where it began, there's got to be a moment of perfect stillness, a place where the slope is zero. And that leaves us with a really cool question to chew on. What if our journey didn't end at the same elevation? Could we still guarantee that our slope at some point would match something else? What about, say, the average slope of the whole trip? And that question, my friends, is the gateway to the mean value theorem and so much more in calculus. Thanks for diving in with me on this one.